Hello, my name is Gaganjit Singh and this is my presentation for PBL Task 3 Game of Name. Firstly, what is Game of Name and how you play it? Game of Name is a very old game. The rules of the game are such. It is played between two players and they have a number of piles of stones or tokens, whatever you want to call them, and each player takes turn removing a number of stones from one pile at a time, and the person who picks up the last stone will win, and the person who has no stone left to pick will lose the game. This is a normal play variant of the game. This in this project I will be dealing with this variant of the game. uh, In game theory, this is known as an impartial game, which means there are no draws in this, no randomness or any chance, no dice or cards involved. The game has finite states, and both players have perfect information about the game and can make any move they want as long as it's legal. Uh, Now the game can be in two states at any time. It can be in balanced or it can be in unbalanced state, also known as N position or P position. N position stands for next position, which means the player who will make the next move will win the game, and P position means the player who made previous move will win the game, which means the current player who which just made the move. And the next point is mathematically proven that if the game is balanced, the next move will always lead uh, the game to be unbalanced. This is mathematically proven and it's always true. But when the game is unbalanced, it can either lead to a balanced or an unbalanced game. I will not go through the mathematics of this in this presentation. It is well explained in the report. Now, one way to tell if what our state is through NIMSUM. Uh, what NIMSUM is just binary addition without carrying. It's similar to performing an exclusive OR operation. One way to practically do it is to count the number of ones. Firstly, we need to have our piles and stones. For example, we have 4 piles and these two have 2 stones in it and these two have 3. Firstly, we convert it into binary, and then with for each pile at one place, we'll check how many number of ones are there. In this case it has 2, so that's even, so we'll write 0 in here. In this case 4, even, we'll write 0 in here. So this state is has NIMSUM 0 and it is a balanced state. The next move will lead it to be imbalanced. For example, we take one stone from this pile, and this will turn this 3 into a 2. And for that, this is how it will become. This will become a 0 here, and it will lead at this 0 will have a 1. So the name sum will be not 0, and the game has become unbalanced. Now the problem at hand is to create a program that plays the game against a human and with a random number of piles selected from between 2 and 5, and the starting tokens will always be greater than 2n plus 1. The approach for the solution. This is how I think this I thought of solution to work. Firstly, we calculate all the possible moves that from first pile how many can, and I will represent it as a list of list in my code. The first integer will denote what pile it is in, and the second integer will denote how many stones to take from that pile. And then for each move, I will check if that move was made, will it lead to NIMSUM of 0. If it does lead to NIMSUM of 0, I will make that move and stick with that move and pass the turn to the next player. This is possible in the imbalanced game position where The name sum is not 0, so the goal is to turn the name sum to 0. And when there is balanced, the name sum is already 0. We can't do much about it. All we can do is make a random move and hope that that opponent makes a mistake and does not play optimally. So we'll have a chance to again make the game balanced. In the code, I'll be using Python. Again, these two concepts to be keep in mind. If the game is imbalanced, we make it balanced. If it's if it's imbalanced, we make it balanced. And if it's balanced, we just hope that the opponent makes a bad move in the turn. This is the flow diagram of how it will work, like basic flow diagram, step by step. Calculate all the possible move, iterate over each move, and check if the name sum after making that move will be 0. If yes, make that move. Then give that opponent's turn, and we will repeat from step 2. Keep iterating over every move. Now the pseudocode for it. This pseudocode is for dealing with the game, asking user which move he wants to make that move. This also deals with validating the move to make sure the move is legal. Sorry. Then we check the game over state, which means is this game over yet? Which means we check if the piles are empty. And then the computer makes a move. Again, check the game state again and repeat until the game is over. One of these function calls give us a true, and we terminate that program at that point. Nextly, pseudocode for how the computer will make a move in a for loop. I mean, we'll be iterating in the possible list of possible moves. We'll be iterating using for loop. Select that move, make that move on a temporary list, which will be a copy of the original list, which will have the data of all the piles of how many stones per pile are there. We'll convert that list into binary after making that move. Then check the name sum. If 0, then good, we make that move on the original list. Now I'll be demonstrating the code for this. Let's set up the board. Let's go with this situation. Let's run the board. I will choose this option first. There's 4 ways of playing in this code. Firstly, let's make a move from first pile. I want to take 7 stones, and the computer chose to take 3 from pile number 2. So let's make another move from third pile. I want again take 7. And the computer chose to remove 1 from pile number 2. And let's go with from pile number 4. I want to take 4, and the computer chose to take 4 from pile number 5. As let's see, from pile number 2, I want to take 3. And here the computer made the best move. It took 1 from 5. As you can see, this is a losing position for us. If we doesn't matter which move we make. From 4th, let's take 1. We lose. I want to also show you that once the computer finds a valid move, finds a balancing move, it will always win. For this example, I will run computer versus computer. So the first player, it found the balancing move. And the second player had to make a random move because it's based on the same principles. Again, the first move found the player, the second one always had to make a random move. Therefore, the first player will win in that case because he was the one who found the balancing move. That's it for code demonstration. There are two more ways to play. Firstly, there's one which is the same as I demonstrated, but the computer makes the first move in that, so it's a bit difficult. And the fourth case in which the computer will make random moves. You can also print the data of moves. I will show you. Let's reset the board to this. I want to print all the possible moves, and I want to print how the moves are getting selected. I will choose the computer to make the first move this time. As you can see, the list of possible moves. The program iterating through every move and finding the move which makes the name sum 0 and making that move. Now back to the presentation. This is another result of the game that I played, and it works 100% of the time. Whenever it is able to find a winning move, it always ends up winning. The limit and constraints of this project is that during the binary conversion, I am storing the data as 4-digit binary number. So the maximum possible stones that I can have is 15. And the second thing is that I am calculating every move when I don't need to, because as in this case, you can see I calculated every move, but it found the winning move at this position 4-3. So I used extra computation for essentially nothing, but this is actually helpful when we have to make a random move. So that is why I end up with this function, this method, because when it comes to making a random move, we need the whole possibility of the list. That's how I thought of it. Can be improved, but that's it for. There are many ways I can think of to improving this, but for now I'm happy with this. Thank you. In conclusion, I want to say that it was in this project I ended up making a program that played a game of name optimally. Also, I learned a lot about game theory and nim sum and using XOR operation. Overall, a very fun project. Thank you.